Welcome back to Mining of Massive Datasets. We're going to continue our discussion of clustering by looking at the CURE algorithm. CURE is an acronym that stands for Clustering Using Representatives. But before we get to the algorithm itself, let's see why we need it. Remember, we've looked at the BFR algorithm, or the Bradley-Fayad-Reina algorithm in the last lecture for clustering really large data sets that don't fit in memory. The BFR algorithm is great because you can scan the data in one pass and obtain clusters. The problem, though, is that the BFR algorithm makes really strong assumptions about the data and about what the clusters look like. The first assumption that the BFR algorithm makes is that the clusters are normally distributed in each dimension, that in each dimension there is a fixed centroid and a fixed standard deviation that each cluster follows along each dimension. The second strong assumption that the BFR algorithm makes is that the axes are fixed. So the clusters then, if you follow both these assumptions, that the clusters are normally distributed in each dimension and the axes are fixed, the clusters that are discovered by the BFR algorithm have this cigar kind of shape that you see here on the left. It could either be a horizontal cigar shape or a vertical cigar shape or a circle, which is kind of a limiting case of an ellipse. But if your clusters actually are not oriented along the x or the y-axis in this case, or along the axis in general in the multidimensional case, but are at an angle to the axis, as I show in the second picture here, that's not okay. The BFR algorithm will not find a cluster that looks like a tilted ellipse. It can only find clusters that look like either upright or horizontal ellipses. And now if your clusters actually look very, very different, like the picture on the extreme right here, where there are two clusters and the clusters look kind of like crescent moons except in opposite directions, those will definitely not be found by the BFR algorithm because they don't look like cigars at all. They don't look like ellipses at all in any dimension. So that's the kind of cluster that will never be found by the BFR algorithm. So the BFR algorithm, even though it's super efficient, makes the strong assumption that the clusters are going to look like the pictures on the extreme left and not like the other two. And we'd like to avoid this assumption and try to find clusters regardless of what they actually look like, because we don't control what the clusters look like in the data. The CURE algorithm tries to fix this problem with the BFR algorithm. The CURE algorithm assumes a Euclidean distance. Remember, a Euclidean distance metric means between any 2 points, we can always find a midpoint of 2 points by taking the average of those 2 points. However, the CURE algorithm, unlike the BFR algorithm, allows clusters to assume any shape whatsoever. There is no restriction on the shape of the clusters. So in the CURE algorithm, any of these clusters, the first, the second, or the third, are perfectly fine. The CURE algorithm can find clusters of those shapes. The difference between the CURE algorithm and the BFR algorithm is that in the BFR algorithm, we represented each cluster using its centroid. Whereas in the CURE algorithm, we're going to use, instead of a centroid, we're going to represent each cluster by a collection of representative points. So instead of representing a cluster by 1 point, we're going to represent it by many points. Here's an example of a data set where the clusters don't look anything at all like ellipses or cigars. So this data, on the x-axis, we have the age of faculty members at a university like Stanford, and on the y-axis, we have their salaries. Now, this is not the actual data, but more a representation of what the data might look like, although it's based on real-world experience. Now, the data points marked by H are salaries of faculty members in the humanities, whereas the data points marked with an E are salaries of faculty members in the engineering departments. And as you can see, it's apparent from the graph here that in the humanities, the starting salary is somewhat lower than in engineering. A humanities faculty member starts at a much lower salary than an engineering faculty member. But as over time, as their tenure increases, the salary of a humanities faculty member keeps increasing and eventually overtakes the salary of an engineering faculty member. Whereas the salary of engineering faculty members increases a little bit with their tenure, but then kind of flattens out. It doesn't increase beyond that. And this is just a phenomenon that has been observed in terms of salaries at most universities. And presumably this is because in the engineering departments, the fields keep changing so much that there is a lot of value in bringing in new faculty with new interests and new new expertise. Whereas in the humanities, I guess you age better as you age. So if you sort of look at these two sets of salaries and you try to cluster them, what you really want in an ideal world is two clusters. One that looks at the engineering salaries, and one that looks at the humanities salaries, and cleanly separate out these two data points into two separate clusters. Now, when you're looking at the data, remember, you don't know that some of these salaries correspond to engineering faculty members and some to humanities faculty members. So the clustering algorithm doesn't have access to this information, but you'd yet like it to find these clusters in the data. Now, it's too much to hope that a clustering algorithm can actually find these exact clusters, because these are overlapping clusters, and most clustering algorithm cannot find clusters that actually overlap with each other, where a single data point is in two clusters. But at the very least, we can hope that the clustering algorithm finds some approximation to these clusters. For example, we might want to discover one cluster there, another cluster there, and a third cluster there. So that would be a nice outcome from any clustering algorithm. And the CURE algorithm can indeed find clusters of this nature. The CURE algorithm is a two-pass algorithm. And let's look at the first pass of the two-pass algorithm. In the first pass, we sample a random set of points from the data set that's given to us. Remember, the data set is really large and doesn't fit in memory at all. It's sitting on disk somewhere. But we're going to randomly sample points from this really large data set. And we're only going to sample enough points that fit in memory. We've covered techniques for sampling in another lecture, so you know how to do this already. Now, once we have a lot of sample points that that we've randomly sampled, we're going to use any main memory clustering algorithm. For example, you can use a hierarchical clustering algorithm that we covered in a previous lecture, and you can cluster the sample points that are in memory using the hierarchical clustering algorithm to create an initial set of clusters. Right? And because hierarchical clustering is a complex algorithm, it can actually find clusters of the nature. It doesn't have any kind of restriction on the kind of clusters that it can find, so it can find clusters of any shape. Now, once we've actually clustered the sample points and figured out the initial set of clusters, for each of those clusters, we're going to pick representative points to represent them. So what we're going to do is we're going to pick a number, k, and let's say 4, and we're going to pick k representative points for each cluster. Now, our goal is to take a cluster like this. Let's say here's a cluster that we found using hierarchical clustering, and we want to find representative points that are as far away from each other to sort of get a good coverage of the cluster as possible. So for example, you might want to, if we find the first representative point there, we might want to find the second there, the third there, and the fourth there. So we have 4 points that are sort of well distributed in the cluster, and they cover as much of the cluster's volume as possible. And we've sort of in a previous lecture we've discussed how to pick points that are as dispersed as possible in a cluster. The technique is to, for each cluster, first pick the first point at random, and then you pick the second point to be within the cluster but be as far away from the first point as possible. And you pick the third point to be still within the cluster but as far away from points 1 and 2 as possible, and so on. And we've covered this technique in a previous lecture. So once we pick these representative points, what we're going to do is that we're going to create these synthetic points. And these synthetic points are obtained by moving each representative point a certain distance towards the centroid of the cluster. Right? So we have the cluster, we know it's centroid, and we have these k representative points. Now we're going to take each representative point and we are going to create a synthetic point that is obtained by moving the representative point a fixed fraction, maybe 20%, towards the centroid of the cluster. And the 20% here is a parameter to the algorithm. So let's look at an example that should make this clear. So here are faculty salary data. And let's say when you run hierarchical clustering on a sample of the data, let's say this is in fact a sample of the data and not the actual data. When you run hierarchical clustering on this, let's say here's the first cluster that's found, here's the second cluster, and here's the third cluster. So we end up with these three clusters that are found by the hierarchical clustering algorithm. Now, once we found these clustering algorithms, let's take one of these clusters and let's say we want to find 4 remote or representative points for each cluster. And let's start with the cluster to the right. And there's the first representative point, let's say it's the one that that we've ended up picking. Now, we want to pick the second representative point to be in this cluster, but as far away from the first representative point as possible. So that's the point we end up picking. The third representative point is going to be still in the cluster, but as far away from these 2 points as possible. So we end up with that point there. And the fourth representative point similarly ends up being that point there. Now, once we pick these 4 remote points for the cluster, we are going to move these points towards the centroid of the cluster. No, we're not actually going to affect the data itself, but we're going to pick synthetic points that are closer to the centroid of the cluster than the remote points that we've actually picked. Now, the centroid of the cluster is somewhere in the middle of the cluster there. So each of these points is going to move towards the center of the circle here. So when we move the points 20% towards the centroid, we end up with these synthetic points. And these synthetic points, or manufactured points, are going to be the representative points for this cluster. And we repeat this process for the other clusters as well. So for each cluster, we end up with k, in this case 4, representative points representing that cluster. So that's the first pass of the CURE algorithm. In the second pass of the algorithm, we scan the whole data set. Remember, so far we've been working with a sample of the data set that fits in memory. Now we go back to the whole data set, which is sitting on disk, and we rescan the whole data set and visit each point P. And we're going to take the point P and we're going to place it in the cluster that's closest to it. And the definition of closest is very simple. We're going to find the point, we're going to take P and we're going to find among the set of representative points of all the clusters, we're going to find the representative point that's closest to P. And we're going to assign P to the cluster belonging to that representative point. And that's it. It's a very, very simple algorithm where we just scan the data in one pass and we place each point in its closest cluster, which is the cluster with the closest representative point. Now, CURE is a very, very simple algorithm as we saw. It just requires a main memory sample and cluster, finding some representative points, and then one scan of the entire data set to place each data point into the closest cluster. But surprisingly, CURE really works well for a large number of use cases in finding complicated clusters of the kind that we saw with the faculty salaries and so on. Our discussion of the CURE algorithm wraps up our discussion of clustering, which we've covered over the past several lectures. Remember that the clustering problem is one where we're given a large set of points with a notion of distance between the points, usually in a very high-dimensional data space. And our goal is to group these points into some number of clusters, with the points that are closer together being in the same cluster. We looked at a variety of algorithms to do clustering. We started with agglomerative hierarchical clustering, where we looked at the notion of centroid and clusteroid. We realized that hierarchical clustering, while it's extremely flexible and can produce clusters of any shape, is really, really complex and it doesn't really work well or scale well to large data sets that don't fit in memory. Thus, we looked at other algorithms that scale well to large data set. We started with the k-means algorithm, Then we looked at the BFR, or the Bradley-Fayad-Reina algorithm, which is an implementation of k-means for really large data sets. But we found out that BFR has certain limitations, so we looked at another algorithm called CURE, or clustering using representatives, that overcomes these limitations.